what we have before us are data for 20 countries on two variables. The variable that I have listed in column B is life expectancy, and you notice it's the Y variable, so I'll treat that as my dependent variable in this regression analysis. And it's average life expectancy at birth in years. Then in column C is the independent variable, which is the level of urbanization in a country, percent of the population that resides in an urban area. What I'm going to do here is use the LINEST function in Excel to generate a bivariate regression model regressing life expectancy on urbanization. Now, LINEST is best used as an array function. So what we want to do is first of all highlight the range of cells into which we will have the results placed. And what you should do is highlight 2 columns and come down 5 rows to contain all of the output that is generated using LINEST. Now, once we've highlighted 2 columns and 5 rows worth of cells, then equal LINEST, open parenthesis, the known Y's, so click and drag to highlight the range or the array that contains the known Y data, the dependent variable, comma, then the known X's, comma. Now there also are constant and statistics options here. I always just put in a 1 for a constant. If you happen to just enter nothing in and just put in a second comma, it will treat it as though the default is to generate the intercept. And I always include an intercept in these models, comma, and the real value of the LINEST function is that it generates a wide variety of statistics that we can use for assessing model fit as well as completing hypothesis tests. So I'll put in another 1, or you can type in the word true for both of those, comma. So known Y's, comma, known X's, comma, 1, comma, 1. Now before you hit enter, you should instead hold down the Control and Shift, and while those are being held down, then press the enter key. Just a typical array formula process. And you notice it is an array formula. As we look up in the formula bar, the array formula is now contained within curly brackets. Now let's go through the output that we have here. Now with the 2 columns of information, if we look in the 2 first rows that I have already put the labels of coefficient and standard errors just to speed up what we're going through here. The very first column reports the coefficient and standard errors for the variable urban or urbanization. The second column reports the coefficient and the standard error for the intercept or the constant. And I'll go ahead and center these and highlight them a little bit. So those first 2 rows that have output, first row is coefficients, standard errors, then the second row. But always it's going to be the first piece of information reported is the coefficient for the independent variable, and the second in that row is then going to be the intercept. Now as we go below those first 2 rows, we see information that tells us about the entire regression model itself. We see the R-square value, which indicates here that knowing a nation's urbanization explains about 43.5% of the observed variation among these 20 countries in terms of expected life expectancy at birth. Then we see below that is the F statistic, and this is found by doing nothing more, and we'll go through that in a moment, but this is the F statistic that's used for determining whether or not the R-square value is statistically different from 0. We then see the degrees of freedom for the model, and the degrees of freedom will always be n minus k minus 1, where n is the sample size, in this case 20, and k then is the number of independent variables, which in this case is 1. So 20 minus 1 is going to be 18. Then we see the regression sum of squares. Sometimes you'll see textbooks or other software refer to this as model sum of squares or explain sum of squares. Whether you see regression, model, or explain, they all indicate that this is the amount of variation we see in the dependent variable that is accounted for by this regression model. And then the residual, or also referred to as the error sum of squares, is nothing more than the amount of variation in the dependent variable that we've observed in this sample that is not explained by the regression model. And in essence, to compute then the R-square value, all we would do is take the regression or model sum of squares and divide that by the total sum of squares, which is just the sum of regression and residual sum of squares. Now, one other piece of information that I've not mentioned just yet is the standard error of the regression, also sometimes referred to as the standard error of the estimate. This is an alternative measure to R-square for goodness of fit, and it measures in essence the accuracy of predictions from the regression model. It's closely related to the sum of the squared errors that we see down towards the bottom here. And we can think of it as sort of similar to a standard error of predicted errors. Now that's not exactly right statistically, but generally speaking, that conceptually is what it is similar to. In that case, the smaller the standard error of the regression or the standard error of the estimate, the better fit the model has. It tends to be referred to less than does R-square, but actually statistically it may be more useful of a measure. But this is how we generate the output for a bivariate regression model and the associated statistics that are generated from this model, from this routine, using the LINEST function in Excel. Now, one of the things that may have occurred to you when looking at the output from the LINEST function in Excel is that while there's an awful lot of information reported here, there's no information that's directly related to hypothesis testing. However, what we do see here is enough information that we can use with additional Excel functions in order to actually engage in hypothesis testing ourselves. What you see below the output is I've typed in the general outline of two common tables that you'll see for any statistical routine and a statistical package for regression. The ANOVA table, and below that the table where the regression model results are reported in terms of the individual variables. Let's show you how we can fill in the information into these two tables from the output that we see here from the LINEST function, and generate all that we need for reporting and interpreting this bivariate regression model. The first thing we'll do is fill in the information for the ANOVA table. What we'll see first of all, with the sum squares regression, this value is reported right here, what I call model sum squares. Others refer to it as regression sum squares or explain sum squares. And right next to that is the information that is the residual or error sum of squares. Now the total sum of squares in any ANOVA table is nothing more than the regression sum of squares plus the residual sum of squares. And by the way, the total sum of squares is nothing more than the numerator for the formula of the variance for this dependent variable. Now the degrees of freedom, k, which is the number of independent variables in the model. In this case, we just have one. The residual degrees of freedom is n minus k minus 1, or 20 minus 1 independent variable minus 1, so 20 minus 2, or 18. That's provided right above the residual sum of squares in the LINEST output. The total sum of squares degrees of freedom is nothing more than the regression degrees of freedom plus the residual sum of squares degrees of freedom. And by the way, if we think about the sample formula for the variance, it's nothing more than n minus 1 So in this case then, our total sample size would be 19 plus 1, or 20. Now the mean squares residual is nothing more than the sum squares residual divided by its degrees of freedom. The residual sum of squares, or the mean sum of squares residual rather, is nothing more than the residual sum of squares divided by its degrees of freedom. Now the F statistic, also referred to as an F ratio, is a test for the significance of the R square value. Is an R square of 0.434 likely to have come from a population where the R square value is actually 0? So the F statistic has a value of, we take the mean squares residual divided by the mean squares regression divided by the mean squares residual. Hence it's a ratio of 1 over the other, or 13.83. Now to ask, is this statistically different from 0? We'll use a function in Excel, f.dist.rt, and what this will do is report the area under the F distribution, which is always going to be positive. So it goes from 0 to the left to infinity to the right. Identifies then the area under the curve that is to the right of a particular F statistic, in this case the value of 13.83. So we identify then the value of that statistic, comma, it has 2 degrees of freedom. What's called the numerator degrees of freedom is nothing more than that degree of freedom for the regression sum of squares, comma, and the denominator degrees of freedom is nothing more than the degrees of freedom for the residual sum of squares. Now we'll hit return, and we see that this F statistic of 13.83 will be drawn randomly from a population where R square value is equal to 0.00157 proportion of the time. Multiplying that proportion by 100, we can interpret it as there's a 0.157% chance that this sample was drawn from a population where the R square value is actually equal to 0. So we would reject the null hypothesis for any standard alpha or probability level. Let's go ahead now and perform the same process for hypothesis testing for the independent variable in the model. First of all, what you'll see is the very first value. Sometimes it's the independent variable, sometimes it's the intercept. I'll put the intercept there. And then also I'll type in the variable name, the independent variable. Now the coefficient for the intercept is reported in that first row, second column of the LINEST output. The standard error for that coefficient is in the second column, second row of the LINEST output. Now the coefficient for the regression coefficient for the independent variable in the model is in the first column, first row of the LINEST output, and then its standard error is just below that. Now for any sort of t-test, what we can do is nothing more than take the coefficient and divide it by its standard error. And implicitly what I'm assuming here is that our null hypothesis is that the intercept, and we'll see in a moment, the regression coefficient in the population from which the sample was drawn is equal to 0. And we'll do the same process, taking the coefficient, minus 1 technically, divided by its standard error. And it's minus 1 because, minus 0 rather, and it's minus 0 because we're assuming it comes from a population where the regression coefficient is 0. Now as far as the probability value, we'll use another Excel function here. That's going to be equal to t.dist.2t, and this is the t distribution for two-tailed. We're employing two-tailed hypothesis testing here, which is standard in regression output of stat packages. And what we're going to do is, first of all, select the t-test value for the intercept, comma, now we identify the degrees of freedom. and the degrees of freedom are going to be what we have here for the residual degrees of freedom, or what's reported up here in terms of the and output from LINEST. So that information is already generated for us. And I'll just click it right here. We see there the probability value is 0.0000. We'll talk about this in just a moment. Let's do the same thing for the regression coefficient. Its t-test value. And its degrees of freedom will be the exact same value, n minus k minus 1. Now it has a probability value of 0.00157. You notice the probability value for the F statistic and for the urban variable coefficient are identical of 0.000157. Let me get that right. And what we see, this will always be the case when we have a bivariate regression, that the F statistic as well as the t statistic probability values should be identical. To interpret this then, if there is a 0.00157 proportion probability that this sample was drawn from a population where the regression coefficient for urban is equal to 0. Multiply that by 100, we can say that there's a 0.157% chance that this sample was randomly drawn from a population where the urban coefficient is equal to 0. There's no relationship between urbanization and life expectancy, which is a fairly low, a very low likelihood. So we would reject the null hypothesis that this sample comes from a population where the coefficient is actually equal to 0 in the population, and instead conclude that this coefficient is statistically different from 0. Now, as far as the intercept, what we'll notice here, let me go ahead and format this cell just a little bit. And what I'm going to do here is come up and choose the scientific notation format. And let me go ahead and make it a little bit smaller so it will be displayed here. Now, it doesn't have a probability value of 0, which would mean that it can't come from a population that is a coefficient of 54.052, a population where the intercept is actually 0. But we see here there's a 0.00000003555 proportion for a probability. So highly unlikely. But what you'll see though is most stat packages report the probability to 4 or 5 decimals. So if you see a 0.0000 probability, it doesn't mean it's not. That is the probability. No, the probability would be less than 0.00001 is how we would interpret that. Of course, another approach to statistical inference that we can use here is the construction of confidence intervals. So let's construct confidence intervals around both the estimate of the intercept and of the coefficient for the variable urban. Come under what I have listed for LL, which is the lower limit in that cell, equal. Select on the cell that has the intercept that's been estimated for this regression model. Since it's the lower limit, we're going to subtract from that to find the critical values of t dot inverse dot 2t, comma 0.05, comma degrees of freedom will be 18, and I'll close parentheses. What this is going to do here, it's going to go out and for a two-tailed test, it's going to take the 0.05 probability value and it's going to put 0.025 proportion of the area under this t distribution up in the upper right-hand tail and the other 0.025 proportion down in the lower left-hand tail. And it's going to ask the question of what are the critical values of t that separate off the rest of the curve from these two extreme areas that comprise 0.05 proportion of the area under the curve. And that will give us then our critical values times, and then the standard error for the intercept. And that would be the lower limit right there, 44.792. Now I'm going to make this formula a little more flexible. Instead of typing in here a value of 0.05, what I'm going to do instead is take 1 minus, and if I take 95 divided by 100, what that's going to do is take 95 divided by 100, which is 0.95, subtract that from 1, and we should have 0.05 left over, which is the 0.05 probability I first put in. So I should get the exact same critical values, hence the exact same lower limit we just computed. But I'm going to make this formula even more flexible. If you'll notice here, I already have a cell that I have the confidence level entered as 95. Hit return, and that's gone out then and found the exact same values for the critical values of t that we did before when we put in 0.05. Let's do the same thing here for the upper limit, equal the intercept coefficient. Now we're going to add to that then the critical value for a two-tailed t distribution. And again, the probability value is going to be 1 minus the content in cell K18, I believe that is, divided by 100, comma, and of course the degrees of freedom, close parenthesis. Now I'll multiply that critical value by the standard error. And there we have the upper limit for our confidence interval around the intercept. We'll do the same thing for the regression coefficient for urban. We take the coefficient, since we're constructing the lower limit first, subtract from that then the critical value of t, 1 minus the content in K18 divided by 100, comma, and degrees of freedom, close parenthesis, multiply that then by the standard error for the regression coefficient. We'll do the same thing for the upper limit. Take the coefficient. We'll add to that, of course, find the critical value for t for two-tailed. 1 minus, again, 95 divided by 100, comma, click on the cell that contains degree of freedom, close parenthesis, and multiply then that critical value by the standard error. And this indicates then that based upon our observed sample of 0.288, it's using a 95% confidence level. It's likely that this sample was drawn randomly from a population where the true parameter estimate for the relationship between urban and life expectancy falls somewhere between 0.125 and 0.451. Now going back to how I constructed this confidence interval formulas here, I can now go back up to my cell where I've 95 entered, and let's say instead I wanted to construct a 90% confidence level. Rather interval with at the 90% confidence level. And right there automatically then recalculates. Let's say instead I wanted to use this 99% confidence level. And right there with one click of the button I'm able to estimate a different confidence interval. And the same thing for 99.9. So that's why I used that more general formula. Let's go back to 95, which is typically what we will report. You can also see down below these two tables I've just created that I've copied the value of the R square from the LINEST output. And also I've reported the sample size. Now the sample size can be found really one of two ways. One, I could have just used a count function and counted up the number of numeric values that there are either for the y or the x variable. But what I did in this case is I took the total degrees of freedom and added 1 to that.